Thank you, Lance, for that awesome. So Amy and I are here to talk to you now about Neo4j for Graph Data Science and the Graph Data Science Library. So for those of you who haven't heard us or met us before, I'm Alicia Frame. I'm the lead product manager for Graph Data Science at Neo4j. And joining us is my colleague, Amy.
Hi, I'm Amy Hodler. I'm Director for Product Marketing and Programs in Graph Data Science. I didn't have this lovely, glamorous shot, but Alicia. So for those audiences who haven't experienced peeps, I thought I would share that I am a big peeps fan. I don't like to eat them though. I just prefer dioramas. If you don't know what that is, you can Google it. I won't take any more time here with explaining peeps dioramas, but we are going to talk a little bit about graph data science, what Neo4j has to offer in the library that we've just announced recently. We're going to do a really fun demo and then take some questions. So with that, I actually want to go back to something that Lance said earlier today. So he made a comment that it's not what you know, that it's who you know, that understanding the forest, seeing the forest through the trees is important. And I want you to think back to the last job that you got, the last job change you had. And it probably wasn't 100% based on your skill set or what you already knew, but it was also based on who you know. So who you knew maybe, introduces you to the right person, or rather somebody who was a couple hops out from you probably introduced you to the right person. Now, the interesting thing is that studies actually show that it's not just who you know, but where they are in the network, which is really interesting and something we don't traditionally think about. So thinking about something that I assume most of us care about is your pay. Well, how are you compensated? And wanting to know, like, how do you increase your own compensation? Network science actually has some interesting ideas or interesting things to share here. And looking at and studying who increases their pay the most over time, they actually found that it wasn't who you might think. That the network structure, where you are in the network, was actually very predictive of your pay, your promotions, and even what kind of reviews that you might have. What they found was that people, and like these people at A and B areas, people near structural holes actually increase their pay more frequently and more over the time of their careers. Now, for those of you who already love graph theory, probably can guess or can look at this and say, those are people with high betweenness centrality. They're bridges between networks. And so they have this tendency to be viewed and compensated more than other people in the network. And they actually call these people structural misfits, or organizational misfits, which makes me feel a little better because sometimes I feel like an organizational misfit, not really fitting in any exact team. But what they said was that that's actually a good thing. That following traditional recommendations to just stay in one swim lane and only get promotions within your group was actually not that valuable. So people with a lot of tight connections inside their particular group were actually less valuable than those people who spanned different groups. They were viewed as less valuable. They were compensated less. And that if you've ever thought about, and this is the only, I guess, probably the only career recommendation for today's sessions, if you've ever thought about changing positions and going to a different group, that's actually really effective long-term. And that lateral moves, even if you go downward in position, actually help you longer term. That's more promising for the longer term. So I bring this example up quite frequently for people because for one reason is it's just not intuitive. It's not what we've been told. It's not what you would assume that would happen. And I think that's why I love network science and why I like graph data science, is because it's just so darn powerful. It can help us see things that we otherwise wouldn't see. So since we're talking about data science and graph data science, it probably makes sense for our resident data scientist to explain what those terms actually mean.
Awesome. So I really like to kind of start this presentation with kind of a level set, because I think to a lot of us who work in the data science or analytics space, the term data science means a lot of different things to different people. And when we talk about data science, what I mean is when you're a data scientist, you're someone who's using data to answer questions. And there are different tools in the toolbox that you can use. It might be algorithms for machine learning. It could be visualization tools to plot your data and communicate what it tells you. It could be statistics to calculate, descriptive statistics, do hypothesis testing to see, what's different, to do forecasting. And it's kind of putting this all together in a scientific way to answer questions. So it's not one thing. It's not, I use scikit-learn to build a regression model. It's a toolbox of a whole bunch of different ways to leverage data to explain outcomes and answer questions. When we talk about graph data science, my short version is it's data science, but better. But what we really mean is graph data science is when you're using relationships to answer questions. So if you think about doing data science with tabular data, rows and columns, pandas land, you really can't look at the connections between your data points, right? You have each data point is a row, each column is a descriptor. And you could maybe painfully hand engineer some maybe 1-degree relationships, right? But when you're doing graph data science, you're really putting those relationships front and center and using the structure and relationships within your data to power predictions. And when we talk about the toolbox for graph data science, that's what Neo4j is bringing to the table. So it goes from things like graph queries, where you've got your data in a graph, you have a question about the patterns that are there, you're using Cypher. It's graph algorithms, like Amy already mentioned, betweenness centrality, where you're extracting information about the topology and clustering of your graph. And it's visualization tools like Bloom, where you're, again, communicating what's in that graph, what does it tell me, what does it show, and you're able to make a visual to represent that. And you can kind of put that together to do everything from data exploration. So what's in my graph? What does my graph look like? To analytics. So I want to run an algorithm and find out how many communities there are. And those communities I'm going to base some decision on. To feature engineering, where you're using graph algorithms or queries to generate features or extra columns for rows and columns land for your predictive model. And so the toolbox for graph data science is really just being able to use the power of graph, these multi-hop connections, to answer questions. When we talk about graph data science, we talk about this spectrum from local to global. And so on one hand, you have really local pattern matching using queries and Cypher to look at real-time local decisioning. So I have a question, I have a graph, my data is in a graph shape, I want to interrogate that graph and answer my question. So it might be something like, I know this person has committed fraud. How many people are in their network up to 4 hops out? I want to look at those people. It might be, I want to find 2 people who've interacted before and they have a third person that one of them has interacted with, but the other hasn't. So you have a specific question, you're looking for a pattern, and you're answering it to make a decision. On the other end of the spectrum, where it's more about global patterns, you have graph algorithms. And this is for kind of this global analysis and this iterative approach, where instead of saying, find me the node that matches this pattern, you're learning the overall structure of your network. You're updating your data with the results of graph algorithms to add more information. And you're using that to make predictions. So this is things like saying, how many clusters are there in my graph? Which nodes are the most important? Where should there be edges that I haven't seen them before? What are the shortest paths? So you have this spectrum going from very specific, I need to find something that matches this, to these unsupervised machine learning algorithms for global inference. And putting those together, you really have kind of the tools that you need to answer your graph data science questions. And so with that, I'm going to pass it back to Amy again to talk a little bit more about the values.
Thank you. So if I think about the conversations that we have with data scientists, a lot of time they're trying to improve what they're doing today. So already have some kind of predictive model and trying to make it more accurate, reduce false positives, and trying to put it in production as quickly as possible, without introducing some kind of risk. And the interesting thing, I think, about what we've already talked about, and probably a little more of what we'll talk about, is that we know relationships and the structure of your data is very predictive. And it's very predictive of behavior, but it's often not utilized a lot. So you have relationships relationships already in your data. They're hiding in your data. So one of the things we like to help people is don't stop what you're doing, but don't throw out that predictive information. So add in the relationships to what you're already doing so you can improve accuracy, reduce your false positive, enhance what you're already trying to predict. Graphs are a natural way to store relationships and to compute relationships. They were created to study relationships, but they're probably different than what a lot of people are doing today. And that's why Neo4j, with our customers actually asking us to help them add in these predictors, because Neo4j is the leading graph database, so asking us to help with that next graph challenge for them in the graph analytics and graph data science space made sense. And so the areas that we see that used in range from a lot of different industry and use cases. I would say here's just a few examples. You'll hear a lot about fraud. Fraud has a data shape, and you can actually look at certain communities and patterns and actually do a better job of predicting and preventing fraud. Things like marketing, whether you're talking about personalizing recommendations or customer segmentation, that's another area that we work with a lot of people. Disambiguation, really important. It's hard to tailor things. It's hard to market to people to get them the best services if you can't tell who they are, especially online when people are often anonymous. So there's a really great session later today by Meredith that will talk a little more about disambiguation if you're interested in that. Another area, life sciences. We also have a talk a little later in the life sciences area by Dr. Jarash. But everything from drug repurposing to understanding customer journeys as well is very important in the life sciences area. So many other use cases, not time to go into each one of them, but you can see, everything from, the fraud to churn prediction to predictive maintenance, cybersecurity just ranges quite a bit. Anywhere you have a lot of data and relationships that are relevant to what you're trying to predict. 3 use cases I do want to call out. One is a really interesting one with Caterpillar using AI and knowledge graphs together, which is really interesting. So they had millions of warranty service documents, and they were able to parse that, use NLP to get the data into a knowledge graph, and then use that knowledge graph to then help inform the AI to learn what they would call prime examples. And that would be prime examples of problems. So if you can imagine everything from a certain sound, like something's making a clunk or a whine, and the certain sound associated with a certain type of equipment that maybe was manufactured in a certain time frame, putting all of that context together for a service call allowed them to improve equipment lifespan and also make, obviously, their customers happier. I mentioned the German Center for Diabetes, DZD. They're going to be speaking a little bit later, but they had, in the diabetes area, they were connecting many research databases, over 50 research databases, hundreds of thousands of workbooks, biosample databases, trying to bring all this together and allow their researchers to see things in a new way, to use the knowledge graph for search, but also use graph analytics and even adding in some AI elements as well to help them see things that maybe weren't obvious before. I talked about those non-intuitive aha moments, but also to give them views that were flexible to whatever their specialty was. So a kidney specialist versus a cardiologist might be looking at things differently. Finally, another really interesting use case is with fraud, doing fraud detection and recovery. There's a top 10 US bank that we've worked with that were having trouble with credit card fraud, which was about 70% of their credit card fraud was actually being missed. It has to do with synthetic identity fraud as well. But they had over 1 billion nodes, over 1 billion relationships to analyze. And using graph analytics, both queries and algorithms together, they were able to find millions of fraud within that first year. So some really interesting maintenance example here, some very life sciences, important medical work, and then also some very tangible financial results as well. What's interesting when we talk to customers and we watch them go through a journey, there's this evolution that they take and that we think a lot of users will take going through graph data science. So starting with knowledge graphs, improving decision support, whether you're talking about human decisions or AI decisions, trying to make better decisions. Graph analytics when they're trying to answer specific questions, trying to understand something that they need to answer today. Graph feature engineering, often using a graph to make predictions about the future. So how can I use graph-based elements to improve what I'm already predicting? And then graph embeddings and graph native learning, kind of a little more advanced. So as customers kind of move forward, graph embedding allows you to do more advanced, more complicated feature engineering, if you will. It's an area that we're working on right now. We expect to have some graph embedding functionality this summer, so really exciting. That'll allow people to do things like do graph feature engineering on an entire path. So an entire customer journey or a patient journey, which is really exciting. Graph native learning is a little farther out. There's some really good research out there, but that's where you're actually doing your learning inside of a graph structure. So it's an area we're watching very closely. So a couple examples, we'll start with the knowledge graph, and where you're doing searches and queries in support of some kind of an expert, whether it's human or AI expert. An example in retail is what I would say even deceptively simple queries that can be hard to do in a relational database management system. So for example, we've got customers, products, we've got subcomponents within the products, we've got locations, people are buying things, and you might want to do something as simple as collaborative filtering. Users who bought one product might also bought another product. It sounds simple, but it's an open-ended pattern match. And if you can think about that from a relational standpoint, you'd have to do many lookups, joins, lookups, joins, lookups and joins, and it can really bog you down to the point of not really being very easy to do, especially when you start getting multiple, a larger data set and have multiple lookups you need to do. In that same vein, if you're trying to traverse a long hierarchy, that can be very difficult within, anything beyond 3 to 4 hops. And we see that quite frequently. And that could be something as simple as a product hierarchy. We've got products with subcomponents and subcomponents with more subcomponents. And you can imagine doing that in a very complex product area, could be very difficult. Or maybe you just want to know if someone buys one product, how likely are they to buy something else in the future? So these are things that you're trying to answer right away. You have a domain expert or an AI system that's trying to make a heuristic decision. So with that, let's look at actually graph analytics, where we're using queries and algorithms, usually in offline data, to understand the larger data set. So we want to understand more about the topology and what is the structure of our data and how can that help us answer questions. And to do that, I'm going to take a quick double click here into the graph algorithms and functions in Neo4j. I believe we're up over 48 or so. You can correct me if I'm wrong, Alicia. We keep adding more, and I keep getting behind. It's all in our docs, but we have quite a few from pathfinding and search that help us find an optimal route between A and B. Think of a supply chain. Centrality, which is all about importance. Most of us are familiar with PageRank, the credibility score that Larry Page helped popularize and is used in Google. But things like that between the centrality I mentioned, who are the bridges? Who controls the flow of resources? Community detection is all about finding communities. So understanding how things are partitioned and grouped in our network, and what are the qualities of those? Are they strongly grouped or are they loosely grouped? Is it a weakly connected component? Link prediction is about understanding and trying to see from a structural standpoint. So looking at the topology of our data, what are the relationships that are likely to form in the future? So you can think of that. We've done quite a bit of material on, you'll see this in our blogs, like trying to predict whether people will collaborate in the future. But it could also be relationships that exist, but it's just not in our data set. So maybe they're missing. The data is missing. Similarity is very akin to a set comparison. So not strictly based on relationships themselves, but trying to understand how similar are nodes based on attributes or things that they do. So maybe they like chocolate cake and somebody else likes marble fudge, and somehow that makes them more similar. So similarity, trying to find nodes that are more alike based on a score of attributes. So an example of how you might use graph algorithms in a retail example, we're going to try to reason about the structure and try to make predictions based on network structure. So for example, connect to components, that identifies, and that's a little red circle here on the screen, that identifies groups of users that are connected to each other, but not the other part of the network. You can think of them as floating islands of networks. That can be very predictive of unique users that maybe interact with each other and perhaps don't like the rest of the group, or just very tightly integrated with each other. PageRank, as I said, was originally used by Google to estimate credibility of a page, but it's really a good measure of volume of transactions as well. So if somebody has a lot of PageRank, that might mean that they have a lot of orders in the system. Or if we're looking at products with a high PageRank, we might be looking at products that have a lot of subcomponents that are ordered for that product. So you can also be used to measure transaction volumes. Louvain is a modularity algorithm that helps identify groups based on their structure, and it estimates that groups that are tightly integrated with each other, have a lot of tight connections, more than what you would expect to see in the rest of the network. So the two little red circles here, if your eyes are really good, you can see that they're still connected to the rest of the group, but they're more tightly connected with each other. And finally, I mentioned similarity. We have a similarity metric that's based on a Jagard score, and looking at these nodes, I know it's not easy to see the little nodes here, but we're basically just identifying groups that have a high likelihood or high similarity score there. So a couple examples of using graph algorithms. If we think about graph feature engineering, you can use graph algorithms or queries to develop predictive features that you can then extract for machine learning. And here we're trying to improve the predictions that our models are making. So again, a quick example here, we're trying to basically combine data, create new meaningful predictors, features. An example might be those clustering scores. Maybe they're part of a certain group, or connectivity measures. You might be able to see here, we've got a graph that is actually using the Bloom visualization tool. We're extracting out information from that. We've got a betweenness centrality score. We've got some non-graphy features as well, like unique shared products. And then we have more graph features like weighted page ranks. So different elements that you can combine together. And then since the example here is a training data set, we have an abandoned cart metric as well. Didn't they abandon their cart? And we can use that kind of a model to train our, we can use that kind of approach to train our model and try to improve our overall predictive quality. So some really interesting different ways that people are using graphs, both for strict analytics, but also for graph feature engineering. And as I mentioned, embedding coming soon, and we're watching that graph native space very closely as well. So with that, I think I will leave it to Alicia to talk about some of the exciting product news that we have.
Awesome. So hopefully by now we've convinced you of the value of graph data science and that graphs are really useful for stuff. And maybe you're saying, okay, but how do I get started? What does Neo4j do for me here? And we like to talk about kind of Neo4j provides an ecosystem of tools to help you do graph data science. So at its core, we have the Neo4j database. Hopefully everyone in this presentation knows about Neo4j, but if not, we're a native graph database. We store your graph data in a graph shape. We let you query it, we persist it, you can update it. On top of that, we have the graph data science library, and that's the product that I work on, which is our plugin that does graph data science. So it has algorithms and a workspace to provide you with the ability to flexibly reshape and experiment with your graph. And I'm going to spend most of the rest of the presentation talking about that. And then in terms of communicating and exploring your results, we offer Neo4j Bloom. which is a visual graph exploration and prototyping platform. So you have kind of my core database. I have tools to help me interrogate, learn from, run algorithms on that database. And then I have tools to help me visualize both the results of the algorithms and the data in the database. So it's kind of a whole package. So today we're mostly going to be talking about the Graph Data Science Library. And you might have been wondering, what is that? So it's a plugin for Neo4j. And there's really two key pieces to be aware of. So the first is the graph catalog operations. And what these are is you have your core Neo4j database, and then the graph catalog lets you take that transactional database and flexibly subset or reshape it into an in-memory analytics graph, which is optimized for analytics and data science and algorithmic optimizations. Think about like lots and lots of global traversals and aggregation. This lets you project your transactional database into the right subset of data, right shape to efficiently run your algorithms. And your algorithms run on this loaded graph, and they compute metrics about the topology and connectivity of your graph. And Amy already spoke to different classes of algorithms. In general, they're all highly parallelized, and they can scale into the billions of nodes. So diving a little bit more into like, what is the Graph Data Science Library? What do we offer you? So really, we have rebuilt the Graph Data Science Library from scratch to have enterprise-grade features and scale. So some of you may have used the Graph Algorithms Library before, which was an awesome MVP put out by our labs team. My team has spent the last year working on that to upgrade it to basically support enterprise production graphs. And so what we offer now is a graph-specific analytics workspace that's immutable and that's integrated with your native graph database. So we automate the data transformations. You just type graph.create, and you pass it either a Cypher query or the nodes and relationships you want to use for your graph algorithms and your graph analytics. It lets you really do fast iterations and layering. So subset your data, reshape your graph, project it, and then taken together, these provide kind of production-ready features. So everything around our in-memory graph is parallelized. We offer enterprise support. Really, the limit is how much memory do you have, not how well can our software scale. So on top of that, algorithms. So what have we done here? So my team has spent the last year working with early adopters and customers and the folks you'll hear from later today to find out which algorithms actually provide the most value, which algorithms answer key business questions and give you the information you need to be able to leverage your graph data. So we've already gone through, validated that these are useful, optimized them, implemented them to minimize the memory footprint, maximize the speed, let you do reasoning about your network structure. And so the idea is that these graph algorithms let you answer questions that you couldn't answer without them. So you have things like structural pattern matching, community and neighborhood detection, influence and risk identification, disambiguation. These are all things where you need to know the relationships between your data points. And the graph algorithms let you flexibly extract this information and these insights on these really large production graphs. So we have customers with up to tens of billions of nodes that they're running algorithms on. If you've ever tried to do this, like me, I spent a lot of my career doing this. Try running, a homegrown, home-cooked algorithm that you've written yourself on a graph, and it's hard. So we've really tried to make this easy so folks can get up and running. And then finally, we spent a lot of time making sure that this graph data science framework is practical and usable. So if you used graph algorithms before, the API could be hard. The error messages were sometimes mysterious. And it was hard to know, did I do the right thing? So my team has worked really hard on simplifying and standardizing the API. So it's really easy to know, how do I subset my graph? How do I reshape it? I learned the syntax once, it's consistent across all the functions. And then we've provided a lot of documentation, training, and examples so that it's really easy to get started. We don't want there to be this like barrier of entry to becoming a graph data scientist. We want this to be easy, useful, and pleasant. Part of that is we spent a lot of time building in guardrails. So we have error messaging. So let's say you try to run an algorithm that expects an undirected graph, and you pass it a directed graph. Instead of just failing, you get an error message that says, hey, you need to pass this an undirected graph. Or if you accidentally mistype a configuration key, let's say I type relationships instead of relationships, then it'll say, did you mean relationships? So we try to make it so you know what went wrong, how to fix it. We also make sure we don't want to fail silently. So if the algorithm runs and it gives you a result, it should make sense. And Mott's one of the engineers on my team, will be talking a lot more about this later today. And then finally, we spent a lot of time making sure that it's easy to explore your graphs and your algorithm results visually. So using Bloom, you can look at those results and say, did they make sense? Is this the question I wanted to answer? So I ran Louvain, I found these communities. Are these communities really reflecting the thing that I wanted to find? Once you've run your data, you've got your data in Neo4j, loaded it into memory, executed your algorithm, you can go over to Bloom and say, okay, let's do the sanity check here. And it lets you also share insights across teams for better collaboration. So we've tried to put everything together to basically make it easy, pleasant, and informative to do graph data science. So we like to talk about what your data science experience is like. And I really love this slide. I've spent 10 years of my career kind of doing data science with graphs. I mentioned those homegrown algorithms. They're not a lot of fun. So if you're doing graph data science without Neo4j, what's it like? So you kind of start from this question of, okay, I've got all my data with rows and columns. How do I make it into a graph in the first place? All of these graph algorithms, they expect a graph to run on. So I've got to transform my data into whatever the format this particular library I want to use expects. And I have to decide which algorithms do I want to use. There could be dozens. There's dozens of libraries containing hundreds of algorithms. A lot of them are very slight variants of each other. Not a lot of documentation. It's not really easy to know what tells me what about what. Let's say you've given up, you just picked one, you said, this one looks good, I like the name. Now you've got to learn the syntax. Good luck. Depending on the library, everything has its own special syntax. It's all slightly different. Let's say you've got that running. Great. Now you've got to reshape your data. So I have my data. I know how to represent it as a graph. I need to build a pipeline to repeatedly reshape my data as a graph into the format to run in this library. I got the library to run. Now what do I do with the result? I have to send it somewhere to a flat file back to my database. This has been an unpleasant experience. So at Neo4j, we want to make that better. So the idea is, guess what? Data modeling, you don't have to worry about it. We're a graph database. Your data is already in a graph. When it comes to which algorithms, we have spent a lot of time understanding, based on users, based on the literature, which algorithms are useful. What do they tell you? Which one do you choose for which problem? And we have the documentation and the tutorials to make it easy to pick. The syntax has been standardized and simplified, so it's consistent and easy to use. The reshaping step, you don't have to worry about. I already talked about that graph.create, right? So you have a single command that lets you subset your full transactional graph into the slice that you want to look at to run your algorithms, load it into memory, execute, and we're a database. So as soon as you get your results, you can write those right back to Neo4j and move them into production. So the idea is the graph data science library makes it possible to do graph data science with Neo4j. And so with that, we're going to do a demo, and Amy will kind of introduce the background information while I set up my Neo4j instance. You are on mute.
I got it. All right. Well, thank you. And I got to say, I just love the little smiley and frowny faces because I've heard you talk about it enough to know those are definitely emotions that represent how you feel about before and after. So
you've seen me make those faces.
I've seen you make those faces, absolutely. So we've got a really fun demo for you guys. It is a retail data, and it's actual data from an online retailer. It's based out of the UK. They provide all occasion items. Think of those as something you might do for, parties or planning of some sort. And later on in the next session, Anurag also has some fun visualizations from this as well. So if you can stick around for that, you definitely don't want to miss that fun as well. But in this data, we've got customers who have transactions of items, and the items have certain categories. Like, is it a toy? Is it a kitchen item, what kind of an item is, and the customers have countries as well. As I said, this is real information. There's 28,000 nodes in 1.1 million relationships. If you want to download and play with this yourself, we will have a link at the end of this session where Alicia has put some of her put the information that's used in a GitHub repository, but you can go to the source as well. So this is based on a paper called Data Mining for the Online Retail Industry. So you can go and follow along there as well. In this demo, we're using Neo4j 4.0, the Graph Data Science Library 1.2. And in the next session, we're going to add to this fun Bloom 1.3 as well. So that's what's in the data. What we're going to do, what Alicia is going to do, is actually first do some customer segmentation. So how do we break our graph into different customers with similar buying patterns? So we want to group people by transactions. So we'll do some similarities based on transactions. We'll then do some community detection. We'll look at Louvain modularity. And then we're going to mutate that graph in memory and then eventually export it as well. Looking at item recommendations, like how would we recommend items? To go down that path, we want to look at what items are co-purchased more and are more likely to be co-purchased together in different groups. And so we'll look at some similarities. We'll look at some centralities, looking at influence, which is interesting if you think about product influence. And then again, we'll mutate this in memory and export what we need to. Step number 3, which is to explore and do the final answer to our business questions, what do I recommend when? We'll actually save that for the next session with Anurag to actually walk through the visualizations and make the final recommendation. So what do you got for us, Alicia? Show us the cool demo.
Okay, so let me share my screen. So hopefully you guys can see that. So here's what I've got. Here's the same schema that Amy just showed us, where we've got customers, transactions, items, categories. Just to show off again, because I am excited about this, we are running on Neo4j 4.0.3. So the Graph Data Science Library 1.2 just came out in preview last week. It will be GA on the 7th of May. And it is the first version that is compatible with Neo4j 4.0. So I'm very excited about this. This might just look like some random text. But anyways, on to the demo. So the first thing we're going to do is, so we have this data set of customers. So this is a business-to-business graph. So these are stores that are buying items in transactions. I want to make some recommendations about, what should they buy, or if one item is out, what should you buy instead? What do I want to promote for you to buy? So the first step that I actually want to do is look at, can I break my customers down into segments? So typical market segmentation, you say, well, I want to look at stores in this geographic region or something like that. What we're doing is we're taking a graph-based approach. So the first thing I'm going to do is I'm going to use my graph loader. So that's that graph.create that I've talked about. And for this first one, I'm going to use the cipher loader. So this lets me use a cipher query to choose the subset of my graph that I want to run an algorithm on. And the first thing I want to check is, do my customers segment out by category of item? So do I have, customers that are just buying sporting goods versus customers that are just buying jewelry? Do I have different categories of stores in my data? And so that relationship between customer and category isn't present in my graph. So I'm going to create it in my in-memory graph using this cipher query, where I say, give me customers with transactions with items in a category. So I'm going to go ahead and click run. And so the trade-off when you choose a cipher projection is it's a little bit slower than a native projection, but it's not that slow. This should finish in about 10 seconds. And what this is doing is it's querying the database, finding the data that I want to run on, and pulling that into memory with just the nodes and relationships that I asked for. As this goes, I created a named graph. So my named graph is called the customer similarity graph category. And this means that once it's in memory, I can refer to it in subsequent algorithms. So as this finishes, I'm just going to queue up the next algorithm to explain it. So there's a couple different things you can do with your in-memory graph. So this is loaded. I've got 4,000 nodes representing my customers and the categories. I've got a whole bunch of relationships between customers and categories based on what they've bought. Now what I can do is there's a few things. I can run an algorithm and I can write the results back to my graph in my Neo4j database. I could run an algorithm and I could stream the results back and just look at them in the browser. The third thing I can do, and this is a new feature, is I can do this mutate function, which lets me update my in-memory graph. So I have a new piece of data available to my algorithms, but it doesn't update my database. So I get to see, I'm going to put this in my in-memory graph. I'm going to use it. I'm going to see if it's useful. So the first thing I want to do is I want to figure out which customers are similar to each other based on the categories that they're buying. And the reason I'm doing this is first I'm going to figure out which customers are similar. And then once I have these customers are similar to each other, I'm going to cluster them. So which clusters of users have the most similar buying patterns? That was super fast. I ran node similarity mutate. I made a new relationship called similar in my graph. Now I'm going to go ahead and I'm going to see what the clusters look like. So if I have different types of stores in my customer base, I should see a bunch of distinct categories. So this is going to run. This is in streaming mode. What do I have? Community 1 has 4,300 customers in it. What does this mean? Basically, I found a single giant cluster. So I don't have different types of stores in my data set. I don't have, these are sporting goods stores and these are jewelry stores. Instead, I have stores that have kind of a finer grained customer segmentation. And that's good, because if I could just say, well, this is a sporting goods store and this is a jewelry store, I wouldn't need to use a graph algorithm, right? So that's not useful. Let's try again. Let's look at, can we segment them on something more granular? I'm going to look at items. So first thing I'm going to do is I'm going to drop that customer similarity graph by category. It's gone now. And now I'm going to load my customer similarity graph by item. And if you look at this, this query looks a little bit different. So I've graph.create, but instead of using a cipher projection, yes, I can. What I'm doing instead is I'm using, let me turn off my camera so you guys can see what I'm doing. Cool. So instead of using the cipher projection, I'm using the native loader. So I'm saying I want algorithms with this customer and item, and I want bot. So I'm saying specifically this piece of my database based on the node labels and relationship types. I'm going to go ahead and click run, and bam, that was way faster than before, right? So before we kind of sat and watched for 10 seconds, if you specify by node and relationship types, it's much faster. So now I have my customer similarity graph by items. I'm going to do the same thing. I'm going to mutate that in-memory graph with a node similarity property. So how similar are these customers based on the items that they're buying? So let's go ahead and run this. And this is going to take a little bit longer because now I have a whole bunch of types of items to compare. So not too long. So now I've compared all 4,300 of my customers, and I've created about 15,000 similar relationships. So let's cross our fingers and try again and run the Louvain stream and hopefully not just get one giant community. So what this shows me, so now I have a whole bunch of different community IDs, and you can see that I have a number of communities that are of decent size. So I don't have one giant community that represents everyone. I have a bunch of communities of kind of intermediate size who represent stores with similar buying patterns. So you could think of this less like the sporting goods store versus the jewelry store, and more like, you know, this store is buying goods that are for this specific market. Maybe this store buys cheaper goods. Maybe this store buys goods that are more aimed at women. Maybe this store buys goods aimed at men. Who knows? So now that I have that and I'm happy with it, the next thing I'm going to do is I want to put that new Louvain community in my in-memory graph. So I can do mutate again. And I'm going to do two things. So I'm going to do mutate to put that new Louvain community in my graph. I'm going to tell it to run on my new similar relationship. Remember, that doesn't exist in the database. And then after that's done, I want to take that new property from my in-memory graph and I'm going to write it back to my database. And I already have Louvain community in my database, so I'm just going to put in new so I don't overwrite it. So mutate property would be Louvain community new. And let's go. And so this is a little bit faster than if I had rerun it in .write mode, because I'm just taking that result from the database, from the in-memory graph, and putting it into my database. I'm not recomputing it. And since I'm happy with this, but maybe I want to understand what this did in memory, we have a new function called graph export. And what that does is it takes my in-memory graph and it creates a new Neo4j database. So what I've done here is I'm going to call it customer segmentation. So all I need to do is tell it the name of my in-memory graph, the name of the new database I want to send it to. Let me copy this so I don't get it wrong later. I'm going to run that, and this is using the Neo4j admin tool to create a new database. And you can see I made a new database called customer segmentation, which has 2 relationships, a whole bunch of nodes, a whole bunch of relationships in it. So let's go to use system. And this will show me I've switched from my Neo4j database to the system database where I can manipulate my multiple databases. I can do create database and just give it the name of the one that I just created. So I'm going to say customer segmentation. This has stood up a new database, show databases. I can now see my customer segmentation database, and now I can use customer segmentation. If I did this correctly, I toggle over here, I just see my customers and my items that were in my in-memory graph. And so if this is a good way of sanity checking, what was I doing when I was mutating, updating that in-memory graph? I can see the bot relationship that I loaded in, and then I can see the similar to relationship that I created between customers. So this customer is similar to this other customer. I'm going to go back to my main database. This was just a fun aside. So if you're doing versioning, you want to do version control on your models, you want to preserve what you are working on to come back to it later, you can use graph export. So I'm going to go back, use Neo4j. I'm back in my main database. And then there's 2 more steps I'm going to just show you guys. I ran these ahead of time and I wrote them to the database. Would be bored to watch me type a lot more. So I've segmented my customer base, and then I talked about I wanted to do item recommendations. So what I really want to do, and I'm going to make this big enough for you guys to see, is once I've dropped my customer similarity graph, I'm going to create a new graph between items so I can measure the similarity of items, but I'm going to look at the similarity of items within each community. So I have these segmented customers. I'm going to see how similar are the items in those communities of customers that have similar buying patterns. I'm going to do the same step where I create a similarity relationship. I'm going to write that back. And so what that tells me is it's kind of this, if X is out, what should you buy instead? Or if you're buying X, what else can you buy? So you can think of it as like a more multi-hop version or a more kind of unsupervised machine learning driven version of your standard collaborative filter. The other thing I would do, so let me get rid of this one. I'm going to pull up this one. So we talked about centrality. So similarity is pretty easy. These nodes are similar to each other based on their neighbors. Centrality is kind of how important is an item based on its relationships. So to do this, what I would load is, again, I'd be using a cipher projection because this isn't hard-coded into the graph. And I can say, well, which customers are buying items together in this customer community? And once I have this co-purchasing relationship, so this item was bought with this item this many times, I can run algorithms like closeness centrality that basically tells me kind of how closely connected is a node to the rest of the graph. So closeness centrality is based on how frequently a node is on the shortest path to between other nodes. And so you can say a node with high closeness centrality has the shortest path to all the other nodes in that cluster. PageRank, Amy already mentioned, is about influence. So like a node with a high PageRank is a really influential node. So you can think of it like a high closeness centrality node is a node that might be driving volume. It's commonly bought with other things. Whereas a high PageRank node on this item co-purchasing graph is going to be based on basically being influential on what else you buy. So let's say I ran these, I already ran them in the background. I'm instead gonna go back here, make this small again, and I've already saved this, so let's do some exploratory queries. So we already worked on creating items that are similar within one community. So what if I want to say, so she claims that these market segments are different. So let me look at items that are similar in one community and not similar to each other in another community. So I'm looking at items that are similar in community 1052 and dissimilar in 2556. So in 1052, I see a lot of things where I've got like plant markers for mint, parsley, rosemary, and there seem to be these like commonly co-purchased. Oh, I'm buying one herb marker, I'm going to buy others. If I look at the other community and I ask the same question, what's similar in this community and not in the first one, I find a whole different set of items. So I find a lot of toys that are kind of interchangeable. So if I buy a blue patch purse with a pink heart, I commonly also buy a felt farm animal hen. These have similar buying patterns. So already it's pretty obvious that the buying patterns in these two communities are different. Community 1052 seems to be buying a lot of gardening stuff together, whereas community 2556 has kind of a mix of toys, accessories, purses, all kinds of cool stuff. So we talked about page rank. So this is how influential is a node. And I want to test out this hypothesis of these nodes are important in one community and not in the other. So let's go ahead and run this. And I can find, well, in one community, this airline bag has a really high page rank. It's really influential. But in community 2556, it's not influential at all. So what this means is these two different communities have really different buying patterns. Diving a little deeper into just a single community, I talked about how centrality and page rank tell us different things. So centrality is like, I tend to buy this item with other items. It has the shortest number of hops to all the other things in my graph. So if you're thinking about a store, this is the Coca-Cola that you throw in your cart when you're doing your checkout. So in community 1052, what items have a high closeness centrality and a lower page rank? So you see a lot of these kind of like cheap items. So you've got passport covers, trinket trays, luggage tags, things that you might be adding in, as filler, like what do you put by your checkout that people are going to pick up and buy? If I want to look at the inverse of that, so which items have high page rank but not high closeness centrality, let's go ahead and run this. And you find some really nice examples. So let's look at the top. We've got cake tins, we've got party bunting, we've got a cake stand. What this looks like is these are people planning birthday parties, right? So if I'm buying a cake stand or a party bunting, this means it's going to influence the other things I'm buying. I'm going to buy other party supplies or other relevant things. So I'm not throwing my cake tins in with everything I buy, but when I buy a cake tin, it's influential on the other things I buy with it. And later on, Anurag is going to do some more exploration. Instead of just text, you'll see pretty visuals. And with that, let's move over to questions, and I'll turn my camera back on.
Great. Thank you so much, Amy and Alicia. What a great presentation to start off our day. We do have some questions that have come in throughout the presentation, and I want to remind everyone else, if you have a question, please feel free to submit it in the questions tab located at the top of your screen. We'll try to take as many as we can given the time we have left, but if we don't get to them all, someone on the Neo4j team will reach out to you directly. So should we start with questions? Do you want to go over some of these resources first? How would you like to do that?
We can go straight to questions and people can read the resources while we answer questions.
Perfect. Okay. So I believe you answered this earlier on in the presentation, but I just want to clarify since it was asked, is 4.0 supported?
I am so excited that I finally get to say yes to that question. So thank you for asking again.
Excellent. And you also, you mentioned something about graph embedding, and is that supported?
So we don't currently offer graph embeddings as part of the product. We are looking to get our first prototypes of graph embeddings out probably early July, so look for them this summer.
Excellent. Thank you. Okay, here's a good one. So is there a difference in the community edition versus the enterprise edition?
Okay, so the difference between community and enterprise is we want to make sure that everyone has access to all of the algorithms, that you have the same algorithms, community, enterprise. Our code is open source, you can download it for free. What we do for enterprise edition is two things. So in community, we limit the parallelization of the algorithms to 4 cores. So you can't parallelize beyond that. Enterprise edition has unlimited parallelization. So when you have large graphs, lots of data, or need your results super fast, you benefit from more cores. So the more cores you have, the faster you can do your computations. And then we also offer premium support, so 24/7 support for our enterprise customers. So if something breaks, if you have a question, if there's a bug, our support team is there to support you when you license Enterprise Edition.
Oh, awesome. Thank you. So I'm going to take one more question. And again, if your question isn't answered, someone will reach out to you. But here's one that asks, how is this different than the graph algorithms library?
All of my favorite questions. So the graph algorithms library was developed by our labs team, and it was really a proof of concept. So are people interested in graph algorithms? Do they like them? What are people excited about? I joined Neo4j about a year ago to turn that into a real product. So we spent a year working with early adopters, who you'll hear from later today, to find out what algorithms really added value, what features were missing, what were their performance requirements. And we've really rebuilt the library from the ground up to meet this. So in terms of like what's different, the 2 billion node limit for the in-memory graph is gone. You can load as many nodes as you've got memory for now. We support multiple relationship types and multiple node types. We've introduced mutability and graph export, which I just demonstrated. We've re-implemented the algorithms. On average, they're about 30% faster in the GDS library than graph algos. We have support. There's a lot of different and exciting things between the two.
Well, it certainly sounds like it. I think that's about all the time we have for this session, but I want to thank you again, Alicia and Amy. And I want to thank everyone for joining us. Please stay tuned. We're starting the next session shortly with Neo4j Bloom. All right. So thank you, and we'll see you in the next session.
Awesome. Thank you all for attending.